last time we were talking about using pure event-driven simulation method, right? Then we have demonstrated this example of creating a pure event-driven simulation with two events, one event, another event, and two messages. Okay, so we see that pure event-driven simulation have these problems. It may require you to create extra events. You need to create every different type of event for different type of actions that you want a component to take. Then it requires you to really think in a non-intuitive way, and it's really hard to reason about the process. And also, especially when you have many different events, this event can happen at the same time, and how they interact is a problem. So it's still very hard to get it correct. Then you need to schedule retry events. So if you cannot send something, then because of the buffer is full, you have to retry in the next cycle by schedule another event. Then if you schedule another event, it's basically even slower than cycle-based simulation. In that case, it's probably better just to use cycle-based simulation, right? So then to solve this problem, we created this method we call smart ticking. So in smart ticking, our goal is to let user to write cycle-based code. So you write a tick function for every component. Then our engine can decide when to tick and when not to tick. And the mechanism is actually very simple, but we think it's a very useful method that can make useful and can increase the performance by a lot if we can skip all those unnecessary ticks. So as a first step, we create a tick event for every component. Right? We create a tick event for every component. Then if we do that, this is basically a cycle-based simulation, but it works on top of an event-driven simulation engine. Then in this way, this is strictly slower than cycle-based simulation, because other than executing every cycle update, state update, every tick of every component at every cycle, we also have the extra overhead of creating those events and insert the event into an event queue and pop from the events. Right? We have those extra overhead. So this method allows you to write a cycle-based code, but is actually not very useful because of the performance trade-off. So then we create this. So if you want to implement this way, this is the code that we can write. For example, here we have this handle function. In handle function, we simply let the ticker do tick, right? And call c.tick later. So this component tick later is calculates the time of the next cycle, next tick time, and schedule an event to let it happen in the next cycle. Now, the next cycle, there will be another tick event, which is this e, then this handle function will be called again. So again and again, these components will tick, right? Then what's in the tick later function is to use the frequency to calculate next tick and make tick event, and consider if it's secondary or not. Then we schedule a tick. If you don't consider the secondary part, this is very easy. We basically calculate the time, create an event, then at the end schedule the event so that it can happen in the next cycle. Okay, so very simple code here. Then we want to make it consider this type of cases. We want to skip some ticks when it's not necessary. So we need to analyze what ticks are not necessary, right? Okay, before talking about that, we have a frequency. This is something that we have not introduced. Frequency is similar to time. It's also a floating point number. So if you consider 1 gigahertz, 1 megahertz, then those are all they're floating point representation, but they're integers, right? They're in the type of float 64. So then we use a frequency to calculate the next cycle. So frequency, this is a Go syntax that, although it's a primitive type, which is float 64, double precision floating point number, you can add functions. You can add methods to this newly created method. You're not adding a method to the floating 64 type, you're adding a method to the frequency type. Now frequency, then we have these functions like next tick, this tick, or n cycles later, these commonly used functions, so that we can easily use these functions to calculate time relevant to the current time. Okay, so there are several functions, but next tick and this tick is probably the most commonly used method. Okay, so for unnecessary ticks, what are the unnecessary ticks? Unnecessary ticks, we think if we tick this component, but this component state will remain the same, we consider they are unnecessary ticks. So if this tick on this particular component has no state update, the internal state has not updated, we consider the tick is not necessary, right? So in what case a tick has no update? Basically, we consider there are two cases. One is this component is fully idle, it's not doing anything. For example, a cache unit, but there's no memory request going through this cache unit. Then we consider it's fully idle, then in that case, there's no point to take this component at all. Then on the other side, we say outgoing buffer is fully occupied. So we know each port has an incoming buffer and an outgoing buffer, right? So each port has an incoming buffer and outgoing buffer. And if this buffer is fully, if this outgoing buffer is full, then we cannot send anything out. We try to send something out, but the port must return an error. So we cannot send, we have to retry in the next cycle. Then if everything that I want to do really depends on one port, or I may try to send two messages and both messages are jammed at the port, then if external environment is not changing, I cannot make progress anymore. Until we have buffer slot, then I can fill in the slot, then I can move forward. So basically I'm stuck at this point. I cannot move forward because I cannot send things out. Okay, so in these two cases, we consider this tick it has no update, right? So how we can detect these two cases? Then we can either test the port and compare the states, which compare the states can be a really annoying thing, that the state of a component can be so complex, right? Then basically we say, if we can use the tick function to tell us if progress is made or not, then I know it's making progress or not. You do a little bit task, if it change internal state, this made progress field can be turned into true, then I know a progress is made, right? So you just do action, action, action. If all the actions have not made progress, then no state change is made, right? If any command that change any internal state or register value, then we consider this state is updated, right? So if there's no progress in one cycle, we consider there's no point to tick again in the next cycle, unless there are external environment changes. So that's our basic rule here. No progress in one cycle, then we'll stop tick. Then when external environment change, we will let it to tick again. So sometimes I may call this, if there's no progress in one cycle, we put it to sleep. Then when external environment changes, we wake it up. Okay, so we can, so when can external changes happens? So since we have two reasons for no update, for getting stuck, then we can have one condition for each cases. So basically, when it's idle, then we consider if there's a new task or a new message arrives. So we know all the communication between components are through messages, right? So there's no function call. We cannot allow one component to call another component's function. This is not allowed in Akita. We cannot do function call. If there's function call, we're bypassing this whole mechanism. Then everything will break apart. So if this component is idle, then a new message arrives. Very likely that a new request needs this component to respond to it. In this case, we're converting from an idle state to a not idle state. Then in this case, we need to wake up. right? So new message arrives, we wake up this component to tick again. Then on the other side, if it's congested because port's outgoing buffer are full, then if at least one port's outgoing buffer comes from the full state to a not full state, in this case, we wake it up. Okay, so it's a relatively simple chain of reasoning that we design this mechanism that when to put it to sleep and when to wake it up. Then, at least for me, I cannot find anything that violates this rule. Basically, we have the whole GPU simulator is implemented based on this rule, and we're not skipping any useful ticks. So this is a rather conservative method that we can guarantee every tick that is useful, we really ticked every component. We're not skipping any necessary ticks. We're not being opportunistic, saying expecting the result to be close than the actual result. We guarantee that you use this mechanism, you can get the exact same result as if you're not using this mechanism. Okay, so same results guaranteed. Because all the ticks we skip, we guarantee there's no state update, right? So let's see how we actually implement this method. Now, remember in the previous code, we have this method, right? This method. Then we make this event happen. We update its internal state. Then we immediately tick later. Then in the updated code, we add a condition check. We ask the tick to return a field. We call it made progress. It can be true or false. This is a Boolean value. Okay. If it's made progress, we tick later. We tick in the next cycle. If there's no progress made, we put it to sleep by not scheduling the event in the next cycle. Okay. If it's not making progress, if it's returning false, so it really depends on the component. You have to tell me if the progress is made or not. If it's not making any progress, we just won't tick in the next cycle, won't schedule the event for you. So it will put to sleep. So for most of the time, if you write a simulator and you encounter a hung error, very, very likely that you're not reporting this thing correctly. Okay. So if you have a live log that your progress is like your time is going on and on, going really fast, then actually that can be an error that you should return false, but you return true. Okay, so this once you know the rule, it shouldn't be very, very hard to determine if it's made progress or not. But sometimes it just at the beginning it's very error prone, and sometimes I need to use breakline debugging to solve this problem. Okay, so made progress, then tick later. Okay, so here you see we introduce a ticker, and what is a ticker? Ticker is super simple. It's an interface that only has one field that has a tick method and returns it takes no field and returns a Boolean value that is made progress, true or false. Okay, this is a ticker. Then the ticking component. The ticking component actually also, remember it's a component, right? It's a component. Every component needs to implement a list of methods, like including name, hooks, whatever, many different fields, but it also need to implement two methods. One is notify receive. So when you receive something. On the other side, you also need to implement notify available. So when a port becomes available, then the port will call this function. So notify that the outgoing buffer becomes available. In this case, we simply do tick later. When receive a message, we tick later. And also on the other side, I don't have that code, but just imagine there's the other part of the code, notify available. I simply do the same thing, c.tick later. So consider this component is sleeping, doing nothing. In one cycle, we receive a message. Whenever we receive this message, we tick later. Tick later means schedule a tick in the next cycle. Then in the next cycle, I can start to process this tick, right? So we put it in the register that belongs to the buffer. Then in the next cycle, I can start to process this message, this request to wake it up. So this part of code combined with notify available is the logic that we wake it up. Okay, so pretty much the whole thing is only 5 lines of code. If made progress, right? And the closing bracket, tick later. Oh, notify port free is there. I didn't see it. Sorry. Yeah, notify port free, not notify available. Notify port free is there. When notify port free, we tick later. Notify receive, we tick later. Now, all the process this request are achieved in the tick function. So in the next tick function, we process the recently received message. Okay, so you see the whole mechanism is only 4 lines of code, but actually can increase the performance by a lot. Especially when we're dealing with, like, say, multi-GPU simulation. For many times, only one GPU is working. Then all other 3 GPUs, if you keep ticking them, it's a totally waste of time. And especially if you have a cycle-based simulation, many people just like to write in a way, say, something like a counter. So for example, every 10,000 cycles, now we do something. Then they may keep an internal counter. So although the tick is not necessary, they just keep this counter, keep increasing. Now, when it's increased to more than 10,000, something can happen. Then you come back to, return to 0. Then start to count again. Now, basically, if you use smart ticking, it's very, you're not encouraged to write this type of code, right? You rather write a code in a way that is data-driven, that whenever there's something arrives, you take some action. Something arrives, you take some action. So you are encouraged to write this type of code. And yes, there are some limitations that you cannot write a code that do something every cycle. And we think this is reasonable because you shouldn't really act. If it's idle, no state update should happen. In real hardware, there may be something that is like a counter keeps going on. But here in the simulator, just ignore that part and use some other method to implement that. And what is interesting is you can actually combine an event-driven and the tick-based component. So for example, if you want to write a component that is mainly cycle-based or ticking component, mainly ticking component, but it just have a long chain of event that can periodically happen. Or if you receive a message, 1,000 cycle later, something will happen. You can actually re-implement this handle method by overwriting this handle method in your component. So you just provide another handle method. So you first check what's the is type. If it's a ticking event, just rewrite this a few lines of code. If it's not a ticking event, write your own event handling process, and you can schedule other type of events. You can combine these two. Although EM/GPU sim, probably a few months ago, like 1 year ago, we still have something like hybrid event-driven or cycle-based. And then more and more, because of the simplicity, we're transiting to pure cycle-based simulation. Okay, so all the components right now in EM/GPU sim are cycle-based, but there are sometimes I do consider moving back to the event-driven simulation because of the performance advantage. Okay. So let's try to look at this logic again in a graphical representation. So at the beginning, or let's say there's a component, I'm only tracing one component. At the beginning of the execution, it must be idle. It must receive the first message then it will wake up. So at the beginning, it's idling. So in 3 cycles, there's no event, there's no ticking happen, right? Then when there's a message arrives in this cycle, in the next cycle, I schedule a tick event, right? So I can allow it to arrive at the previous cycle or anywhere between these 2 cycles. Yes, we can have some arrows to allow this message to arrive, but most likely in most simulator, we're writing, this message always arrive at the boundary of the cycle. Then if a message arrives at 1 cycle, then we will schedule another event in the next cycle to wake it up, right? So wake up when message arrives. Then we'll keep ticking, continue to tick if it's making progress. We'll tick, tick, tick until one point there's this tick returns a false and saying it's not making progress. If it's not making progress, we don't really know the reason, but it cannot be more than that 2 reasons. One is idle, one is congested, right? So we don't really know the reason, and we don't care about the reason. So we just keep idling. Now, when there's another message arrives, we will just opportunistically wake it up. Hopefully, we can catch up something. But in this case, it's still not making progress. In this case, we pretty much know that the reason is because it's congested, right? So when a new message arrives, we tick again, just to try if we can make progress or not. Probably we can make progress, or probably we cannot. Then, if we keep moving on, at some time this port tells me I'm become available. Then we'll keep ticking, tick, 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 tick until it's not making progress anymore. So if, for example, if we fully process this event, this transaction is fully processed, then after it's fully processed, we have nothing to do. Then we'll become just at the end, we'll have an empty block here, then we'll stop there, then we'll not tick again because it's going back to the idle state. Okay, so wake up when port is available. Then, so our goal is we only perform a small portion of necessary ticks. We only process a small portion of unnecessary ticks, not necessary ticks. I only perform a small portion of unnecessary ticks. When we will process these unnecessary ticks, is when the end, right? At the end of a chain, that this one will tell me it's not making progress, or some external event happens, but it's not triggering the right reason, or at the end when it will stop tick again, when it becomes idle again. So we may sometimes still have some unnecessary tick, but we can avoid most of them. Okay, so I want to introduce one concept called back pressure. And back pressure is a common term for simulator. And not only for simulator, it's a term for any type of computer architecture. So like many people, if you develop a simulator, many people will ask you how you model back pressure. Now in Akita, we model back pressure using this message and port system, using buffers to handle back pressure. So what is back pressure? Suppose we have a chain of requests, right? A chain of components. Let's say if this is a core L1 cache, L2 cache, and DRAM, then it's a chain of components. And the area of each of them have some buffers. Then, so let's say at some point, one component may not be able to process fast enough. Now, if it's not, the processing speed of a component is slower than the injecting speed of the request arriving on this component, its buffer will build up. When it's full, this connection that sends buffer from the outgoing buffer, send request from the outgoing buffer to this incoming buffer, have to stall. Stall is a word that says this has to pause and has to wait. Then this buffer starts to build up. Right? When it starts to build up, when the outgoing buffer is full, this component needs to stop, needs to pause, and cannot make forward progress anymore. And then eventually its incoming buffer start to build up because it cannot send out things. Then eventually this connection is building up and this buffer is full, and eventually the topmost component is jammed up. So this is represented by in real hardware, say your DRAM is slow. Your DRAM is slow, you're not getting enough data. Then in your GPU, you can send a lot of requests out. And you can send a lot of requests out. Then eventually you cannot send more requests. And you have nowhere to store it. You have to store things. And for computer architecture, it's different from the network in a like computer network that dropping some frames and asking to resend is okay. For this type of network, you cannot resend. You have to wait until you have a place to store it, then you can move forward. You have to wait until that point. In that case, the core that executes instructions may stop. Okay, so this component, like the core may stop, and this behavior is called back pressure. So the buffer pressure propagates backwards from downstream to upstream. It's a different direction as how we send the messages, right? So then when buffer pressure frees up, then hopefully for some reason this can start getting faster to process, or it can process something. Then this one will free up some buffer slot. Then that one will move down. Then the free up is going backwards, right? So must be the most downstream. The downstream element must free up, then the upstream can free up, then can move forward, right? So this is the free up process is going from downstream to upstream. So because of this reason, we actually have this mechanism that we call availability back propagation. Although it's not really a new concept because it's still this part of code. Let's say in a port, we have notify available, right? So ports notify available is the connection calls ports notify available, saying, oh, this connection is available. You can start to send something to me, right? Then for a connection, this port calls notify available. The port tells the connection that this port is available. So the connection will put something into this component, into this port. Then component also have a notify port free. So when this port from a full state to a not full state to have buffer slot available, it will call the component. It will tell the component, say, oh, I have a buffer slot free. You can try to inject something to me, right? So by using these a few functions, we're actually making a chain of availability, just as this one that I like this buffer freeing up process. Now we're notifying backwards to wake up components so that they can be waked up at the right time. So let's see how it works. So let's say when this component calls retrieve incoming, right? This component calls retrieve incoming, and this buffer slot becomes available. Then it wakes up the connection. It notifies the connection by the port, because the port calls connection notify available and tell, okay, this port becomes available, right? Then the connection, if you consider connection is nothing special but the ticking component on its own, it will tick, tick, tick whenever it's possible. So this connection will start to tick again and try to pull information, try to pull request messages from this buffer into this buffer, right? So this connection will move our data here, will actually call the retrieve outgoing message, right? This connection calls these ports retrieve outgoing. Then it will remove one element from the port. Then the port will call components notify free. So the port is waking up the component, saying you can wake up and start to inject the request to me. So then these components wake up. Okay, so by doing this way, we're having these wake up messages, wake up calls going backward, and this wake up is done by function call, not by sending messages. Okay, by doing this, then we let this component to run again, then this becomes available. And it's the same process at this side to wake up, keep going upstream. The wake up signal keep going upstream. Now, whenever there's a buffer slot available, we wake up the correct component. This is how we implement this mechanism. Okay, any question? No question? So in the rest of today's lecture, I have two examples, one simpler example and one more real-world example, and see how we write a ticking component. Okay, the first one is the ping example again. So it's basically the same ping example, but we're trying to implement in another way. So remember, this is the same slide as before. Then when there's a start ping event, we send a request to ping to receive side. The receiver side receive this message, schedule an event by adding a delay, and send the request back to ping response. Now we have seen the problems of this process, so we try to use ticking component to re-implement A and B. So A and B are the same component, right? But we re-implement this component and see how they are actually implementing here. So since we're converting A and B to ticking components, we don't really need to specify the event, right? They're all replaced by ticking request, ticking event. Then we still need the messages. So this is also copy paste from the previous slide. The messages won't change at all. We still need to send the exact same messages. Okay, so let's create a component and see how this component is created. So this is a component. Remember, we call every component just simply comp. Then the folder that wraps this component, the folder name should be the component's name, right? Then in each folder that defines a component, we should have a comp and we should have a builder. Okay, we can talk about builder later, but at least this part is the component implementation. Then we have it's embedding a ticking component, right? Then it's embedding a middleware holder. We'll talk about middleware later. So most of the MGPSim or Akita's components still not using middleware yet. This is a relative new in V4, new feature in V4. We'll talk about why we want to use middleware later. And then it only has one port, and we call it the out port. It sends out, so we call it out port. There are some internal states. You can consider the internal states are the registers that belongs to this particular component. So for example, we record current transactions, start time of all the pings that we send out, the number of pings need to send, next sequence ID, and the ping destination. So see, this destination is a remote port, right? This is a destination. It's a remote port, and in V3, we have this one just simply as sim.port. Then many people, even very internal people, like very experienced people, try to initialize this ping destination port as part of the component itself. So since this is a remote port, right? We have A, this is A, this B. Since A need to send this ping to B, right? So from the perspective of A, then A dot out port. This is A dot out port. And this is A dot ping destination. Okay. This is the destination where I want to send the ping. It's not my own port. Previously, I just simply kept the sim.port there, kept a reference for destination. And many people got really confused. Then they start to do something that A dot ping destination, new port. Then this is not right, because you should instantiate it when you create B. You shouldn't instantiate this field when you create A, because it doesn't belong to A. Right? So by renaming it to remote port, which is simply a string, a name. So I don't think anyone will still have the confusion. Okay. So then we do tick. Then you can see this tick is basically a middleware holder.tick. There's only one middleware, and there's a tick function. You can just imagine everything here is written in this tick function, and there's no difference. Okay. For this case, you just imagine this part of code is there, is in the tick method of the component itself. We'll talk about why we want to use middleware later, but here basically there's no difference. So as you can see, the tick function. Now, first start to see this type of pattern and how we implement this method. So one question for you. Why I need to write made progress? So let's say, let's read this code a little bit. Made progress equals false. I assume it's false. Beginning, I assume it's not making progress. If any part is making progress, if this is true, right, send the response. If I'm successful, this send response will return me a true. True or false is true. True or false is true, then this is true. We don't care the rest. Then made progress will remain true for the rest of the function. So any of these 4 stages is true. Any of these 4 stages is true, then the final made progress is true. If all of them are false, the final return is false. Okay, this is a very, very common pattern in MGPU sim and in Akita. Almost all components are written in this way. So quick question. Can I write something like this? Made progress or equal m.send RSP. Or I can write made progress equal to m made progress or m.send RSP. Can I implement it in this way? So basically, why I cannot swap these two?
Because it's true.
Yeah, right. So in Go and in most of programming languages syntax, if you have an or method, if you flip, then the first part, if the first part is true, then it will consider the final result is already available. So there's no need to evaluate the second expression. Right? There's no need to evaluate second expression. So we have to make sure we evaluate this one, then or made progress. We cannot flip it. Okay. So this is the program languages rule. At least for Go is true, and for most of language, I actually don't know any language is not using this rule. But for most of language, definitely this is true, and we have to write the important part at the beginning. Otherwise, we may skip some other parts. Yeah, at the beginning, I didn't notice this part. Then it took me a very long time to debug why some stages are not executing. Then after that, I never make this mistake. Then, okay. Another thing. Intuitively, you may think we want to process. Intuitively, you may probably write in this order: send ping, process input, count down, send the response, right? Or let's make it simpler. Let's say in a core, in a CPU core, if you have pipelines. Now, although we're going to talk pipeline later, but let's say if we need to do action, store something in B, and if we need to do some action, A action, store a result here, and B action will take it and store it in another register, and C will take it. And consider these are A, B, and C. How we should order these actions in the code. So we intentionally kind of order it the other way around, right? So for them, process input should be the triggering event, but we intentionally implement it at the end. Why is it? It's a common thing. Action orders. So if something happens later, we need to execute them earlier. Why is that? Let's look at this example. So we have a combinational logic, right? So you can calculate some result and send to this register, store in this register. In the next cycle, remember, if you have a register in digital design, it can only take, so in cycle 1, you generate some result, then store in this register. Only in the second cycle, this combinational logic can observe your previous output, right? So these registers are considered cycle boundaries, right? If I do something like this, in cycle 1, in order implementation, right? If I call this one first, then call this one, then call this one. In cycle 1, combinational logic 1, it will get a result here, right? Then I call the second one. I call the second one to execute. It will detect what's the value here, what's the state here. Then we'll immediately pass data here, right? Because in program, I first execute this part, then I execute this part. When I execute this part, it can already detect the state change. So if this is something in the buffer, for example, I can already detect it in cycle 1. But in real hardware, I can only detect in second cycle, right? So in this case, if I'm executing in order, I'm moving this data to here, right? I'm using this input and calculate the output. That is, in cycle 1, and when I execute combination logic 3, I put data here, and I already can generate the output. But if the total time is 1 cycle, it only takes 1 cycle to pass through 3 stages. On the other side, if I call it in the reverse order, in cycle 1, combination logic 3, it will detect nothing. It will put nothing here. Then combination logic 2, it will detect nothing and put nothing here. In combination logic 1, it will put result here. Now we go to second cycle. Cycle 2, CL3, it still cannot detect anything, right? In this case, cycle 2, CL2 will get the result put there. Then cycle 2, CL1, because there's no input, then we are not doing anything. In cycle 3, CL3, then we eventually can get this result out. So the total is 3 cycles. And in real hardware, it will take 3 cycles. In simulator, it will also take 3 cycles. That's why we're implementing intentionally in a reversed order. Every stage in a reversed order. Okay? Comfortable with this design? It's a common trick of simulators to have to implement the other way, because it's just the program you execute in order, and every instruction, every function call can see the state of the previous instruction function call. In real hardware, it's just it's impossible, right? You cannot see the previous. All the things will execute in parallel, but in simulators are executing in order, so we have to write the other in the reverse order. Okay, then finally, when we talk about middleware. So without middleware, we can just simply write a code in tick. Just directly in the components tick. Then I will say, is my component representing the state or representing the action? Then I always have this concept that when we write a code, write a piece of code, when we write complex software, object-oriented software, we should separate state with action. So we try to have some class that is action only and some other class that is state only. Then middleware are actions, or you can consider their combinational logic. Components, other than this like gluing part that defines whatever that is owned by this component, is state, and those are state, or the registers that belongs to this component. You can see in transaction level, in cycle level simulation, not RTL simulation, we just simply record a time, which is pretty much impossible in digital circuit, right? But here, this is just Like we can record whatever we want. And as long as it's possible in RTL or in digital circuit, we just simply do it in a simpler way. Like array, like undefined size of array is impossible in real hardware, right? In real hardware, all the sizes of arrays must be defined at the beginning. So anyway, these are state. So we're trying to separate state with actions, right? And also, this is a super simple component here, but there are some very complex components that we write in MGPU sim. For example, there's something called command processor in a GPU. The command processor is the CPU within a GPU. It actually controls all the components. So command processor receives the command from the CPU and controls all the components for the rest of the GPU. So it's a really complex thing. It can define different things. For example, it can define how the threads are mapped to each, how the thread are mapped to each core, and how how memory is placed, how memory is migrated from one GPU to another. Now, how we can flush the caches to guarantee synchronization. So it's very complex thing. And eventually, I write super long code for this single component. But there's a separation of concern. For example, for how to map the threads to each core is one part. How to map the memory from one GPU to another is another type of logic. So I want to split them into two middlewares. So middleware is definitely borrowed from network domain, and it's a typical thing for, I don't know if you have heard of chain of responsibility principle. Not principle, this is a pattern. Chain of responsibility. So what is a chain of responsibility? In some book, they simply call this middleware pattern. Okay, how many of you heard of this chain of responsibility pattern? Okay, only a few of you. So let's try to, in the rest of this course, I will try to teach you a few more patterns that's commonly used that can help decoupling the code. Okay, so let's say this is something called middleware holder. It can just consider this is a disk array or something, right? So we have a middleware here. We have a middleware. We add a few middlewares. Now, so when there's a message arrives, this middleware will try to process it. It can process it or cannot process it. If it can process it, then we consider the task is done. So it really depends on how the middleware holder is implemented. So if we can process this message, we're done with this message. If it cannot, it will pass through and try to get this one to process. Then if it cannot, it will pass and let this middleware to process it. This is a chain of responsibility. So if I cannot process it, we'll pass it to the next one. So what's the advantage here? So for example, here, if I have something like, let's say a cache replacement policy, like a cache least recently used. For example, this is something that we'll teach later. But I guess most of you at least already know a little bit about what it is about, right? I can either, like, whenever I have cache, when I have no space, which one I evict from my cache. So do I evict the least recently used, or I can do random. I can just randomly evict something, right? So if this slot is designed for these two things, now I can simply replace this part without impacting other parts. The other parts can still use the exact same code, but I very easily to replace it with a alternative policy here. So this is why we want to use middleware pattern. Although in MGPSim, you don't really see the power of middleware pattern much at this stage because we're just gradually transiting to a middleware style implementation. But here we're using middleware, and there's only one middleware here. Okay, so it separates action of different aspects. Then, in other words, if you are considering patterns are concrete solutions, right? If we consider principles, we're also trying to fulfill this principle called single responsibility principle. Then this is the solid S, okay? And the whole solid principle goes around O, so we'll talk about O later. But let's go with S and ID. We have talked about interface segregation. We have talked about dependency inversion, right? So this is S. So each class, module, or function should have one responsibility. Then this is hard to understand, but I think either understand is a class should have only one reason to change. So for example, I change the policy, right? If I write the whole cache in one part, if I write the whole cache in one part, I may change its policy, right? Its replacement policy, or I may change its timing, like how long time for the cache access. Those are two different things that we may need to modify this cache. Now, in this case, the policy is implemented here, and the timing is implemented in the cache middleware itself. So it's a separation of concern. Okay. So as principle, it's really hard to say that if you fully fulfill this goal or not fulfilling at all. It's just you go gradually towards like fewer responsibility and fewer. I don't think there's one way that you can say, oh, I fully align with S principle. There's really no one way to define what is a single responsibility, but at least you should try to separate the concern. Okay. Then let's go to sendPing, how we implement sendPing. I'll go through this part really quick and only highlight the important part. So this is how we implement sendPing method. The sendPing is part of the tick, right? So we have some internal state, say number of pings to send. Then we define that we can send, if we want to send 10 pings out, we send every cycle. And this cycle really depends on the pinger, the ping unit, the ping component frequency. Let's say it's just 1 second, 1 hertz, or 1 second, 1 tick. And then simply here we record how many ping that we need to send. If it equals 0, we have nothing to do, we return false, right? Still this principle, we consider special cases at the beginning and we try to return as early as possible. Then we create this ping message. Remember here, both source and destination are remote ports. So this out port should call this as remote to convert it to its name, to a remote port. But this ping destination is already a remote, we don't need to convert it. Then we try to send it. If we fail, we simply return false. We tell that, oh, it's not making progress here. Right? We try to send, but we cannot send. Then we return false. Right? It's still not making progress at all, right, at this point. But if it's true, still, we write here, consider special case, and we try to avoid else as much as possible. We don't write else. We use return instead of else. Now, I call this point the critical point. So after this point, all the things can actually happen. What happens is we record the start time, right? Append the start time, number of ping need to send minus next to sequence ID plus increment by 1. Okay, those are the real actions, and this send is another real action. Okay, so at the beginning we check if this action can happen or not. Then at this point, it's a critical point, and then we make these things really happen. Okay. So the process input is very similar to the previous one, but at least we pick incoming. If there's nothing, there's no incoming message, we simply return nil. We don't even do the rest. We return early. Return nil means return false means there's no progress. There's no state update here. Here the ping process ping request and process ping response. Let's see how we process ping request. Is basically we create something called a transaction. Now a transaction is a struct that bundles these two things together. It's a request and cycles left. Remember, we say we want to delay for 2 seconds, right? 2 cycle or 2 seconds. So we say, oh, cycle left is 2, right? And we append it to current transactions. Now we know there's no condition check, right? The condition check is actually here. The critical point is here. Now, once we know there's something, we can always process it. And here, the output retrieve incoming, we take it so that we don't need to process next time. Right? Then, remember there's a 2 cycle, right? There's a start with 2 cycle left. So we just count down. Previously, with cycle-based simulation, we directly schedule an event. But here, we simply use a countdown. If it's a very long one, you can also schedule an event. But since only 2 cycles, it's easier to do countdown. So basically, here for every transaction in every cycle, if the cycle left is greater than 0, we do cycle left and minus minus. When we really reduce the cycle, we report made progress is true. We made progress. We change the internal state, right? Now we expect the take to happen again next cycle. Then finally, send a response. And when we want to send a response, we still do. We say, if there's no current transaction, we return nothing. We return false, right? Then for current transaction, we only look at 0. We only look at head. If the cycle left is still greater than 0, that means the delay has not arrived, has not finished. We still don't do anything, right? Then we start to build this response and set the source and destination. See here, the destination is the source of the original request because we're sending back, right? So my source is always my output. Destination is what the request tells me. So this actually supports multiple, several pings, several components connected together. Then finally, we do output.send. We try to send. If it's not successful, we still return false. Nothing happened at this point. In next cycle, just try to reconstruct this message again. And eventually, this is the critical point. We know this is done. Now we simply remove the transaction. This is pop it from the beginning. And remove the 0. We only keep from 1 and on. Okay. Then this is a critical point, and we return true. We made progress, we return true. Okay. Then finally, the last part is process ping response, and it's easy and it's always successful. There's no condition check. So at the end, we simply retrieve incoming. One thing you need to be careful that we need to somehow match the original request with the response. So we have a sequence ID here. Then this current time. So current time reduced third time is the duration. Then we can print it. Okay. So hopefully I can let you feel that this implementation is much more straightforward and easy to implement. Right? There's a very clear pattern about how this thing is implemented. I don't know if you can find the pattern. So the pattern, first check if this condition if we can process it or not. If we can process it, then we process it. Okay. Any question? Are you okay with this simple simulation? Okay. Have another. Am I going too fast? No. It's okay. We have another example. This is a real example that's really used in the simulator in MGPU sim. It's called reorder buffer. So we see more resource constraints. Previously, we only see resource constraints in the send message. If we cannot send, that means the buffer is full. Then we return false. So you will see the more you see, the easier that you find the pattern and how we implement the component. Every component is implemented, no matter how complex, is implemented in this way, in this pattern. Okay, so we have a core, the CPU core or GPU core. We send a request A to cache, and if it's a cache miss, then we forward this A to DRAM. Right? Then if it returns, before it returns, the core may send a request B to the core. And if it's a cache hit, then the cache may directly return B before A, because A is not completed yet. Now for some time later, DRAM can respond A, then the cache can respond A to the cache. Right? If you look at this as a time order, the order of the request and the response are interrupted. Right? So we cannot guarantee that the send order, the response order is the same as the send order. And for some core implementation, this is okay, but for some other core implementation, this is not allowed. Whenever this is not allowed, we add a reorder buffer in between. Okay, so reorder buffer works in this way. We send A, then the reorder buffer simply pass through A to the cache, then send to DRAM. Then we send a B, it also pass through this cache, pass through and send the request to the cache. Now if B returns, we first hold B because B is not in the right order. So the return buffer holds this B. Then when A returns, we know, okay, A is at the front of the buffer. We respond with this A. We respond A. Then we know A is responded and B's data is already there. It's stored in a reorder buffer. Then we return B. Okay, so this is a reorder buffer. This is probably the simplest component in MGPU sim, and it's rather easy to understand the implementation. So how reorder buffer is implemented? Now I'm slightly simplifying the reorder buffer. So we have the top port here, a bottom here, right? Top port receives request, and bottom port sends request to the memory unit that can at least provide the data. Then response come back from the bottom port, bottom port. Then the final response go back through the top port. Okay, so it has two ports, and internally it has a buffer. These are the requests. So how it works is by having a few stages. Now we first have a top-down stage. Top-down takes request from top port and send. On one side, we send it through the bottom port. On the other side, we inject it into the buffer itself. Okay, top-down. Then parse bottom takes request from bottom port, then take the response from bottom port. Just you can consider read only for now. Then take the data from the bottom port. I changed the spelling here. I forgot to change it the slides before. Then a process response from the bottom port, and we find the corresponding transaction, and we simply put it there. Just record. Oh, you see the data is available. The data is there. Then finally, we have another stage. We call it bottom up. The bottom up only look at the head of this buffer. If the data is there, it will generate response and send through the top port. If the data is not there, it will just keep waiting. Okay, so then we only set it to say something like 1 response per cycle. Okay, this is the design of a reorder buffer. So then let's read the code together. And these are few lectures are about code reading. Let's read code together so that you can understand how this is implemented. So reorder buffer is in this way. So as you can see, it's a ticking component itself. And this is a V3 implementation, or we probably change it to V4, but not fully change it to V4. So something that we have to change is changed. Something that we haven't changed are not there yet. So for example, bottom port should be a remote port, right? It should be a remote port, but we still use the old way. So this is something that we haven't changed yet. So it has 3 ports, control ports. Control ports is responsible for something like drain, reset, or pause, continue, some control signals. We don't consider it at this point. And there's a buffer size, number of requests per cycle, some configuration. And at the bottom, we have some state. This is a map. This is a linked list. And then it's flashing is a Boolean 1-bit state. Okay, so some state. And all these state then were really implemented in a way that it doesn't have to be exact same way as how hardware is implemented, but it's more in a way that how we can easily match the original request when the response comes back. Okay, so let's say tick function. We don't have middleware here, just tick function. And tick function, other than processing control message, we do flash. If it's not in a flashing state, we run pipeline. So pipeline itself is a regular execution. Within run pipeline, we do this. Number of requests per cycle is how many requests that you can process in each cycle. So it's a little bit more complex that can process multiple requests each cycle. Now, for the same reason as I talk about the pipeline order, I have to process this state for n times, this state for n times, and this state for n times, right? So, but just ignore these 4 loops. You can say bottom up, parse bottom, top down, reverse order. Okay. Run pipeline. So the thing that I want to talk is how this 3 part is implemented. You can see the function, the code is not very long. It's very readable. At the beginning, when the buffer is full, you see here, this is use function name instead of comments. Right? We don't want to write comments, but it's full. It's clear enough. It's as if it's a comment. When it's full, we return false. Nothing can happen. Right? When it's full, I'm top down. When I'm doing top down, I want to inject something there. If it's full, I don't even try to read something from the port. I cannot do anything. I just return false. I'm not making state update. Then if there's space, I check the top port. If there's any incoming request, if there's no request, I still return false. I cannot do anything. There's no request, so I'm idling, right? Then I'm taking the request. I'm creating a transaction. So I'm only creating the transaction. I'm not really adding the transaction yet. Okay, I'm creating the transaction. Then this function within this create transaction, we already create a request. So request to bottom. This is a request that we want to send. The request to bottom dot source equals to my bottom port as remote, right? It's through my bottom port. So my bottom port is the source. The destination we already know is the bottom unit, is the other unit. It's included in create transaction function. Then we try to send it. I have annotate. If I cannot send it, if there's an error, that means it's congested, then I cannot move forward. Then I will retry. Right? I will retry. Simply do false. Then in the later, this request is still in the top port. Right? I haven't taken it out. I take it out in this function, retrieve incoming. I haven't retrieved it, only picked it. Right? Only pick it, so it's still in that buffer. So if it's in that buffer, if it's in that buffer, the next cycle I will retry it again because it's in the head of the buffer. The add transaction. Oh, so here, this is something I call a critical point. We have addressed all the constraints that I know this transaction can move forward. Then I make things happen. I add the transaction to this central buffer. I retrieve incoming, destroy it from the input incoming buffer of the top port. Then at here, we do tracing. Like we trace, okay, this event happened. Okay. trace, don't care about, don't worry too much about trace. We'll talk about trace later, next lecture. But here, just only look at these two parts. This is really happening. When it's happening, we return true, and we made a state change. Okay, so see the, I hope you can see the pattern of how this ticking component is implemented. Yeah, add a transaction and remove request from port and eventually do tracing. Then let's look at the other two. I don't have annotation here. Parse bottom. It's basically the same principle. It's probably even simpler. When we parse bottom, we first pick from bottom port. Okay. If there's no response, nothing we can do. Return false. Otherwise, we get a response. This get response tool gets a string which is an ID. Which is an ID that of the original request that we send them to the bottom. And using as ID, we can use this map to find this transaction element, right? If we find it, if we don't find it, simply discard it and return true. So sometimes like resetting may cause this thing to happen. Not finding the original request to happen. So if we find it, we add this, we get a transaction, the response from bottom equals to response. We put the response, we record the bottom, record the element there. So record this black dot, right? This black dot. So transaction.rsp from bottom, response from bottom becomes available. It's no longer new. Now we do trace. The thing really happened, and eventually we return true. Okay, so the critical point is here. So finally, bottom up, we check the transaction.front, the buffer front. If the element is not even available, that means the buffer is empty, we're idling. We return false. Now, if this transaction, we get this transaction, if response from bottom is not available yet, that means the data is not available. Then in this case, we return false. Okay. Then duplicate the response. So all our requests are disposal, one-time use. So we clone a response, we set the source and destination, we send it through the top port. Still, if it's not successful, we return false. But if it's successful, line 20 is the critical point that we'll delete this transaction. We're fully done with this transaction. Then we trace it, we return true. We know this happened. Okay, so I see two rather big examples to see how these components are implemented stage by stage, action by action, right? And all these actions, you see, you can just imagine they are combination logic that reads from register. What are registers? For example, transactions. This is a linked list. It's a set of register that I can read from. Right? Then this response I get from the here. This response I get from the port. You can consider these are from registers within the bottom port, right? So just take the register values and write the other set of register values, or change the register values at the end of this function after the critical point. I make changes to other register values. It's just not in a way of changing 0 and 1s, but we're changing in a higher level style. Okay, so in the next assignment, then you're going to write some component like this. You can either use pure event-driven or use cycle-based. Okay, and I think that's all for today's lecture. Any questions? No? Okay, now I will see you on Thursday. So we'll spend one more lecture in simulation. Then components part is done. The core part of the simulator is done. Then the other things, there are several holes that I need to fill, like why we need secondary events, why how trace works, how hooks works, those like how to use Akita RTM, how to use Dyson, the visualization tool. That is something that we're going to cover in the next lecture.